Thank you for the nice introduction. I think at least there's one sheet I don't have to show you anymore. But he told a lot about my CV. And the last years, more and more, I'm asked if I somewhere in a country, can you give a lecture? And then it doesn't matter what the topic is. And why? Well, it is more to present me just as a live person. You have heard my name in many lectures, I hope, about the formula from 1988, so that's quite a long time ago, the Eurotop overtopping formula and the book on breakwaters. But then I think if I have worked more than 40 years and you know my name and I'm here for you, can I tell you a little bit more than just a topic and give you a presentation? Is it working? Yeah. Okay. So do I have a message for you at the start of your career? I have more than 40-year experience. You are even in education, so your career has to start, and then you have to work for 40 or 50 years, so everything has to come for you. Is there a message for you? Well, let me first tell what happened during my life. I was lucky, I think, to get a significant research project in the beginning of the 80s. Many tests. Delft is a good company for research. I did, I think, quite a good analysis, came to a new formula, and I thought that formula would be valuable to other people too. So first what I did, I sent my thesis to all well-known people in the world, and you have some of them here in the Meer corridor, the pictures on the wall. Some of them I have known, and I sent them my thesis. That were the people at that time that were well known. I only made 2 papers out of my research. One was the paper with the scientific background, with the analysis, with the tests, and ending with the formula. But then I thought, okay, the formula is more difficult than another formula. I have also to show how to use it. So the second paper was, look, here is the formula, but how can you use it in a deterministic design, and also, 1988, in a full probabilistic design. And that is what I showed, and I think that combination and making these papers and sending the PhD all over the world, well, within 2 or 3 or 5 years, maybe even quicker, everybody used the formula, and it got my name. I didn't know that it would happen, but it simply happened. And I was not yet 40 years, I was indeed 33, 35, quite young, without gray hair. And you know, in Asian countries, certainly in Japan, seniority comes with gray hair. You cannot be a senior if you have no gray hair. So I had indeed Japanese visitors, and they didn't want to believe that I was from Meer. I was way too young. You know. But it happened. Then I think this is a part of my life, my work, that is working cooperation and make it freely available. Don't keep it for yourself. And I think Eurotop is a good example. We were a group of researchers in the European Union. We got money from the European Union. We had to work together, and we did nice research, and we got a lot of good results also on wave overtopping. Then my idea was, well, we are a small group, we know each other, we know what we have got, why not sit together and translate the research into application? Because that's a big step. There are a lot of researchers who are not able to do that. But I think we had quite some experience, and we were able to do that, so we made the Eurotop, put it online for free, and it became immediately the overtopping standard in 2007. And it still is. We have a second version from 2018. But it was nice to work together and gift it to the community. Well, the book on breakwaters. You know, I'm on one side a scientist, the other one I'm the engineer, the one that applies the research. But every scientist would like to write a book. But writing a book costs a lot of time. People have asked me, why don't you write a book about design of breakwaters? And I said, okay, if you pay me for 1 year, 1 full year, I'll do it. Nobody wants to do that. They want that I do it in my free time, and that's not what I want to do. And then I met Sigurd Darson from Iceland. He had built about 25 burn breakwaters, a very specific, tiny subject in the coastal engineering world, the specific breakwater, the burn breakwater. And in the time I was working, I had done quite some tests, so I had a scientific part, he was the practical part. There was hardly any guidance on Breakwater, so it was a tiny subject, we could do it together, and we did it, even though it took 5 years to write this book, because we had to do it in our free time. And that means that sometimes a year we didn't do anything. You cannot take 1 hour and then write a little bit on a book. You need a week or so, concentrate, and then you can do something. But we succeeded, and after 4 years we had the book for 90% ready. We went to the publisher and we said, okay, we like to publish this book, and every publisher would like to publish the book, but they would like to keep it for themselves. And we said, at some time, we would like to have this book free, so that people can download it instead of buying it. And of course, we realized that the publisher needs money from publishing the book. So after 3 years, we were able to put it on our website. And you may not put it on your website for free or whatsoever, but you can go to my website or Sigurd Larsson, his website, and you can download it for free. I think we have sold 300 books, something like that. There are more than 5,000 downloads. And I think that is important, much more important than we sell a book, because the income from the book is maybe 1% of the cost we made to write the book. You never get rich from a scientific book. Hey, that was so if you want to have it, then look at my website. There's much more than that. I come back to that later. And then my message for you. Well, I was in the ICCE, the International Conference on Coastal Engineering. Every 2 years we have that very important conference in 2016 in Antalya in Turkey. And they asked me, can you come with a quote? And then I made this one. It is better one quality paper that makes you famous than 10 papers that just increase your H index. And you are at university, you have to publish and publish and publish, but I think maybe one paper less, but the other paper much better. Quality. And cooperate with your colleagues. That is very important. Cooperate with your colleagues, make your work valuable to others, and then you will have a pleasant and rich career. That's my message. So that was not about this topic. I will now go to this topic. Stability of rock-armoured slopes against wave attack. The parameters of rock slopes, the examples of rock slopes and pictures, stability equations, the original one from 1980. How to use it. Because the easiest is just to take the formula, put in the parameters, have the answer, and yeah, I'm finished. No, you're not finished. That is not design. I'll show you. And then in the recent years we have changed the formula a little bit, and then the stability at shallow water, that is a topic that is really hot like now, also at this university. I will end with that. So the parameters on the rock, this is a big rock, about 15 tons. Really a nice and big rock in Denmark. You recognize. Oh. So how do we define a rock? Well, in a diameter, a nominal diameter. It is not the 3 sizes on an average of like that, but it's really the weight, the mass divided by its mass density, so that's the volume, and then to the power 1/3. So actually it's the cubical size of this rock. So whatever shape it has, it doesn't matter. It's the cubical size, the dn is very well defined. And for rock, of course, every rock is different from the other. So we go to the 50% value, and that is the dn50. So rock, 50% of the mass is smaller, 50% is bigger. So there is a range, a radii. Well, we have mass densities 2,600 up to 2,700. That is the normal range. If it is lower than that, you have a less quality rock, but sometimes you have to work with it. If you have basalt, it's even much heavier than this. Concrete is mostly 2,400. For concrete units, you have always the same size, so the 50 disappears. Then you have simply the nominal diameter, dn. So the diameter is important, but also the mass density is important, and the mass density of the water. Seawater is heavier than fresh water, so that makes also a difference. So we go to the relative buoyant density, the delta, which has the mass density of the rock minus the mass density of the water, divided by the mass density of the water. And that comes to more or less 1.4 or 1.6 in most situations. And if you combine the delta in the DM50 and we go to the wave attack on the structure, the waves, then we come to the stability number. And this is really an important number. If you know the stability number for your structure, you know what is the size of your rock. It is as simple as that. So the HSO delta DM50 is very important. Well, what I said, every rock is different. So you have a grading between small rock to a minimum limit and a larger limit. We have the rock manual, and that says we have a nominal lower limit and a nominal upper limit, and at least 90% should be bigger than this value, and 70% should be on this. Between 70 and 90% must be here. So a little bit maybe smaller, a little bit maybe larger. They don't say anything about the M50. I think that is a pity. We have to improve this, and there are papers on this, because we need an M50 and a DN50. So a rock grading is very often defined by simply this one and that line. So 3 to 6 tons means we have 3 tons here, 6 tons here, and probably 4.5 tons somewhere in between the M50. So 10% may be smaller than 3 tons, and 20% may be bigger than 6 tons. So it's not very long specified, but it should be in the ranges. Then breakwater or coastal structure has the armor layer, that is the big rock. It also needs an underlayer, the layer under the armor layer. We also have filter layers, and there's many people mix it up, filter layers and underlayers. But this is simply a layer under the big rock. You need a smaller rock underneath it to support the big rock. And the practical guidance for breakwaters is to have 1/10 of 1/15 of the armor layer. So if we have 3 to 6 ton with 4.5 ton average, then this could be 300 to 600 kilograms, something like that. It's not a fixed rule, but if you have to construct a breakwater, it takes some time. You first make the core, then the underlayer, and then the armor layer. There is time between making the armor layer on top of the underlayer. So if you have some waste during construction, also your underlayer should stay stable. And that is why we go to the 110 to 115. So it's a practical rule for breakwaters. And then that gives you a permeability of the structure of 0.04. I come back to that. E is 0.04. Sometimes you have embankments, so you have first sand, and then you put it in geotextile, and then you want to protect it for wave attack. And that means that you have a very small underlayer, thin underlayer, small rock, very small rock, only 4 to 5 times that of the armor layer, so it's really small. And it's only to prevent that the big rock punches the geotextile. A big rock of 3 to 6 tons, you put it onto a geotextile, it may be damaged, and you don't want that. So it's only for that. But that structure is less permeable, so that SB is 0.1. We also have other parameters for the structure like the crest, but the main thing is we have an armor layer, an underlayer, and something underneath. Could be a core, could be sand with the geotextile. And this is an example of such an embankment. So here we have sand, we put a geotextile, small rock, thin layer, and then we put the armor layer on top. That's an embankment. So B is 0.1. Well, the rear side is also very important for breakwaters. If you have more or less a low crested structure, then you know that the waves will overtop. The armor layer goes from the seaside to the crest and partly to the rear side, and that is stable. Sometimes you have a quite high structure, and then you say, okay, I terminate my armor layer here, put a concrete wave wall in a path. You have also access to your breakwater. Here you don't have access to your breakwater, unless you are a goat that goes from stone to stone. But here you can come with a car or bike, or you can walk. The only thing is, if this is high enough for design conditions, yes, could be, but suppose that you have a stone that is a little bit bigger than design conditions, then the overtopping increases, and this is not really designed, certainly not for waves, because the rear side there are no waves, but also not much for wave overtop, because you don't expect wave overtopping. But if it happens, you're lost. This is the most catastrophic catastrophic failure you can have. This is from a model test from the Breakwater. We had the aquapos on front, completely stable. Actually, also the wave wall was completely stable. We had a little overtopping for the 1 in 100 years condition. And then I said I want to have 20% more, the overload. I accept damage, but I don't want to have failure. But at 20% higher wave height gave quite some more wave overtopping. So much that it attacked the rear side. And in reality, it was 3 to 6 ton rock, so quite big rock. And the waves and the volumes in the waves were so high and large that it attacked the rock behind. And then you get erosion below it, this becomes unstable, and if this happens, then you lose your breakwater. We terminated the test here, but you can see if we go on for 5 minutes, everything is gone. So very catastrophic, and it not only happens in a model, it shows you that it's very good to do model testing. Eh? It's much better that your design fails in your laboratory than in reality. So do model testing if you are responsible for the design of a breakwater. This is a real structure. After a small hurricane, the hurricane made landfall in the wrong position, so the highest waves, where it was a small hurricane, the highest waves were direct into the breakwater, maybe a little bit more than design conditions. The breakwater was 8 meters high, and after the storm it was at sea level. So it's very, very large damage that completely fails. And then the problem is you have to create a new breakwater. But you have not a fresh area, you cannot simply design a breakwater. There is something underwater, there is a lot underwater, and you cannot take it away. So you have to design on top of a failed breakwater. That's quite an experience. So, the notional permeability factor, which I invented in 1988, I said if waves come to a structure, to an arm layer, which is porous and permeable, waves can go up and can go into the structure, and they can go down and also go into the structure. So what is underneath the armor layer determines also stability. So if we have an armor layer to the diameter stick here, 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 we can also make a dash line here, and then we have everywhere the same armor layer. And we can have the same waves running up. But then, if we have a very thin underlayer, and then we have an impermeable, say, geotextile with sand, then all the water has to go up into the armor layer and through the armor layer again. So all the wave energy has to be taken by the armor layer only, and not by the rest of the structure. So that's what I call PS.1. The other side is if we only have big rock, only armor layer, the whole structure is big rocks, then you can imagine that the same wave that it runs up, but there are large holes, so it simply goes into the structure. So there's hardly any run down. It may go up, and less than in here, and there's hardly any run down. So all the energy, or a lot of energy, is going into your structure instead of onto your armor layer. So this is the most stable, and we call that PS.6. Then I did quite some tests with an armor layer and a core, quite big core, no underlayer, but quite a big core, where the ratio in diameter was at 3.2. A real structure often has an underlayer, so like this armor layer, underlayer, and then a core, and we call that PS.4. So if you design a structure, a breakwater, and you make a drawing already, then you have to look at these four and say, where is my structure? Is it a normal breakwater, is it an embankment, or is it somewhere in between? And you have to estimate what your p-value is. That is how it works. When we have a rock structure and we get damage, the damage will be around the water level, the erosion hole. And the size of that erosion hole actually gives you the damage. So we have to measure the profile. Sometimes we also count the number of, certainly with concrete units, we count the number of units that comes out, not the profile. But for rock, we very often measure simply the erosion area. And if you divide it by the nominal diameter to the square, actually it's the number of squares with the nominal diameter that fit into the erosion area. That is what we call S. Oh, here we have a test. I think it's the 1 in 3 slope. Rocks very regularly placed. Quite big waves on it. You see some rock moving. not being displaced, but moving. There's also some rock that has been displaced here, so there's really some damaged area here. You can see that the waves are quite high on such a rock slope. And then you can profile the rock structure. There are different ways. This is fully automatic, simply by profilers. At my time, 40 years ago, we did this. We had the same system, but we did it by hand, and then it moved 4 centimeters automatically. But we put it down by hand, and we pushed the button, and then we had a measurement. It was at that time. Now we do it more and more by laser. Laser can have many more profiles. This is repeated 3 times, so we have 9 profiles, and then we average. With a laser, you can have the whole 3D structure and then make an average. So I think the technique improved quite a lot. But still, this one is used. So if you measure the damage, we have also to say, what does it mean if we have a certain damage value? Well, we have different slopes of the structure. 1 in 1.5 is the steepest we can get, I think, for a rock-armoured structure. 1 in 6 is very gentle. Sometimes we have it for an embankment. And 1 in 2, 1 in 3, 1 in 4 are in between. Initial damage, no damage, is not SE0. Because SE0 you cannot measure as an erosion profile. So there must be some settlement, some compaction, and already some rock that goes away a little bit. And then we can measure the erosion hole. And SE2 is really start of damage. Hardly anything happens. If we have a longer structure, because a more gentle structure is also longer around the waterline, then we can say SE3 is start of damage. If we go to failure, and failure means that somewhere there is a hole in the armor layer where we can really see the underlayer. It's not that the whole underlayer is free, but here and there we have holes that we can see the underlayer. That is what I call underlayer visible. Failure of the armor layer. Not necessarily failure of your breakwater, but failure of your armor layer. Well, that is SS8 for the steeper slopes, 12 for 1 in 3, and 17 for the more gentle slopes. And intermediate damage is, of course, in between. And this is what you have to use for design. It is not enough to have one value for wave height and one value for the damage and say, this is my calculation and now I did a good design. I come back to that. Well, the rock-armoured breakwaters, how do they look like with rock? So this is a specific breakwater in the UK. They have quite some tide. So with low tide, the breakwater has no waves, has no water at all. But during tide, you can see there will be some water depth and waves, and I think with the storm surge it may be even higher, and we are even overtopping. You can see the big rock also on the rear side, so it is well designed for wave overtopping. Australia, quite a steep slope, 1 in 1.5, and you see that the kind of rock, the shape of the rock is different. It's more sharp. Seawall in Ibiza, it's not sharp. You can directly see that it's a different quality of rock, but it looks good, placed well. Also more sharp, and I think the stone comes from Norway, I think, very good rock. You see the train here, so if we have a high storm surge, waves here, at least a lot of spray going over, but maybe even water coming over, could be a problem for the train, but not for stability, but for wave overtopping. Denmark, we have also an example from Denmark, 1 in 1.5 slope, quite big rock. So this is how it looks like. Here we are in British Guyana. This is in the north of South America. They lost their woods, mangrove woods in front of it. There is no better breakwater than a good mangrove wood in front of your structure. It dampens the waves, but if that is gone, and it happens here, they need the rock structure. They made the rock structure, it was not 1 in 1.5, it was really 1 in 4, so it is gentle slope, because it had soft soil. Everything was quite soft here. And this is the problem they had. This is the crest. So this is the original crest, and here the crest is gone. You see the underlayer. And if you see it from the seaside, this is the original structure. Nice 1 in 4 slope, straight. And here you see the crest went down, very gentle slope, and even the toe went up. And I was here to tell what happened here. Well, what do you think? What happened here? Is it the waves that did the work here? Not really. But what you see is a really typical slip circle. The geotechnical problem. The soil was already soft, and in this area it was really soft. So the weight of the rock here made it a nice slip circle. So the crest went down, the toe went up, and now we have a gentle slope like this. And my question is always, what can you do to improve this? What do we have to do? Because that's the other question. First you have to explain what has happened, and then what can you do to make a good structure again? Well, I will not ask you, but the best is, this is a little bit unstable, and it could also happen here. This was unstable, it was very unstable. But if you have this slip circle, and the rock went, now it is very stable. Yeah? So don't do anything on here, because this is stable. Maybe it doesn't look like nice, but it's very stable. The only thing you have to do is to put extra rock here to have the original crest level again. That's all what you have to do, and you have to stay. This is the most stable part of your structure. It was the least stable part, now it's the most stable part of your structure, by the failure. If you go to Qatar and other countries in the Middle East, you very often see a rock like this. This is not randomly placed, just put a rock, that is what we normally do. This is pitched. Each rock was taken, selected, and put in such a way that it looks like a nice, smooth layer. From engineering point of view, it's not good. But your client decides. If your client says, I like this, you have to do this, you know. And if you are a contractor and you didn't know, and you thought you can put your rock just randomly in 2 layers, and you have to pitch them all, that's not good. You should know that beforehand. So be careful in these countries, they would like to have it like this. And maybe if you know that and you have to design this, you also have to do the model test like this. Otherwise you test it with randomly placed rock, and here it is differently. Okay, there's another guy, he's very famous, that's Hudson, you know him. He's already from 1958 with his formula, he was 30 years before me. And this is his equation. Looks a little bit difficult, but we can write it in a very easy way. In the Waterways Experiment Station in Vicksburg in the United States, they have a model shed where they have models for testing stability of breakwaters, and this was there, and that you have to make a picture of it. So this is the original formula. We can write it as a stability number. So the stability number is only has a relationship with the slope angle. That's all. The more gentle the slope angle is, the more stable your structure. The other thing you need to know, what is the coefficient for this structure, whether it is rock or tetrapods or cubes or whatsoever. So as soon as you have the KD value, you know the stability of your structure for start or damage. So very easy to design. This is indeed a formula where you take the parameters and you find the D and 50 directly for start or damage. The only limitations that Hudson had were only 58 weeks. He had no random waves, he had regular waves. There was no technique yet for random waves. So it's not blaming him, but there was no better technique. He looked at the influence of the wave period, but he didn't find any influence. And I checked his work, and yes, there was, what he did was no influence of wave period. But of course he had regular waves, and each wave is the same. So if you have 100 waves of the same height, well, your structure is at an equilibrium. But in reality, you have small waves and larger waves, and one big wave in the sea state. So storm duration is important. The longer the storm duration, in reality, the more damage you will have. There is no real description of damage level, just start of damage, designed for this, very easy. And he used monocoque and permeable structures only, and there are more structures with rock. I'll not tell you about all my tests and what I did. These are the formula, and probably you have seen them before. There is one for punching waves, one for stretching waves, and that is the kind of waves that how they break on the breakwater, on the slope. Punching waves means that the wave really breaks onto your slope, onto the rock. And stretching waves means that your structure is steep enough, or your waves are low enough that the wave just goes up and goes down or goes into your structure, but it doesn't break. So there are two formula, and you have to find the point where they meet each other, and then one is plunging and the other is for researching. I would like to show you a little bit what is in the formula and what kind of influence. So we have this stability number like Hudson, and this is the same formula where we have a coefficient. The permeability factor is in there, and also there is a coefficient like the KD factor, but now it's a real value, one value. There's a relationship between the damage and the number of waves. The storm duration is given in the number of waves. So you need to know what the duration is, you need to know your mean period, and then you can calculate the number of waves. You see S is the square root of the number of waves. So that's the square root is like this. So the longer the sea state is, the less the damage will increase. It will always increase a little bit. That is one. And then we also have a relationship between wave height and damage to the power 0.2. And we can also reverse it, so damage is a function of the wave height to the power 5. So I'll tell you about this one and a little bit about this one. That 6.2 is a value. But we have scatter. In all the tests we have scatter, and we have to describe scatter always. In all the tests we are doing, the formula without scatter is not a good formula. You need to know how accurate you are if you design. So here you see the Gaussian curve, and it means that well, you could have a standard deviation from your test, and if you take 1.64 times the standard deviation plus or minus, you are at the 5% lines. So if you take that, then you have the 90% confidence interval. And that's always nice if you have a design line. Draw also the 5% lines, and you know that 90% of your data should be in that area. So 6.2 and 1.1 could be stochastic variables, and with a normal distribution. And the standard deviation is 0.4 and 0.08 for 6.2 and 1, or the variation coefficient is 6.5 and 8%. And this gives you then the confidence interval, or the 5% lines. So with this, you can do a full probabilistic design if you want. You can also take a partial non-safety factor and do a partial probabilistic design, whatever you want. But what I do mostly, and what I like mostly, is to make damage curves. So we have that damage as a function of the wave to the power 5. That means it's a power curve with the exponent of 5. And that gives you a damage curve. And all the other parameters gives you where this damage curve is. So we have wave height here, damage here, and you have two examples. One is for slope angle 1 and 2, quite steep, with a long wave, 2% wave steepness. The other one is 1 and 3, a little bit more gentle, but with wind waves, steep waves. And you see the big difference. This one fails already before this one has any damage. The only difference is a 1 and 2, 1 and 3 slope, long wave and short wave. But you see also when the damage starts here at about 2.3, 2.4 meters, and you have failure of the underlayer visible around 3.2 meters. So it gives you a range where your damage happens. Damage curves is always nice. And that is also what I use to make a design for a structure. First of all, there is not one design waveheight. There are more design waveheights. You have to look at the wave climate. And then you have waveheights that happens quite often. It will certainly happen in the lifetime of your structure. So you take a 10 years waveheight, and they happen depending on 50 or 100 years, it may happen a few times. You don't want to have any damage for that. Then a 50 to 100 years waveheight, that is what you often take as a design waveheight. But it could be that there are higher waveheights. You never hope that a 1 in 1,000 years waveheight will hit your structure. But sometime it will happen. So you have to be prepared for it. And of course you cannot design for no damage at all for such a waveheight. So you have to look at waves that happen very often, or quite often, waves that maybe happens once in your design period, and you have to look at an overload where you hope it will not happen, but it may happen. And then you say here, no damage, acceptable damage, a little bit more than no damage. Here, no failure. You may have a lot of damage, you may have to make a repair, but you don't want that the structure fails. You may have damage. So actually there are three criteria here. Not conditions, these three, and say what kind of M50 you get. Select a grading, because an M50 is not yet a grading. Grading is if you buy it from a quarry that is existing, it only sells you some gradings. So you cannot choose your grading yourself. Only a dedicated quarry. If you make Breakwater, you make your own quarry very close by, you can decide on your own gradings. But very often, you have to live with the gradings that you can buy from the quarry. 1 to 3 ton, 3 to 6 ton, 6 to 9 ton, whatsoever. So, and then you make a selection on the grading already, and then you make more calculations with the damage curve. I'll show you. Suppose that we have a slope angle of 1.75, a permeability of 0.4, that means a breakwater with an underlayer and a core. 10 years wave height is 2.3 meters, the damage, the design wave height 100 years is 3 meters, and then the overload is almost 20% more, it's 3.5 meters. We say no damage at all for 10 years. This is for a little bit of damage. You do a sensitivity analysis. You can do it for the wave period, you can do it for the p-value, you are not sure about the 0.4, you can take 0.3, 0.4, 0.5, and see what is the influence. If you are not certain about a certain parameter, just vary it and then make the damage curve and see where it is. If it stays below the line, no problem. If there's a large variability, then you have to be careful. This is the way you should design the rock structure, the rock-armoured layer, and not just taking the formula and filling in and find an answer. Well, how do my formula further work if you compare different slope angles? The breaker parameter, the way the waves break on the structure, are quite important. Here we have the lines that they are higher. You have the stability number, also the damage level and number of waves. The stability number, the stability is here. The higher the line, the more stable it will be. The smaller the size of the rock can be for the same wave height. Surging waves, non-breaking waves are here, and the plunging waves that are these lines. So in this area, the type of wave breaking on the structure changes from plunging to surging if we have a steeper slope or we have a longer wave. The gentle slopes are here, 1 in 6, then 1 in 4, 1 in 3, 1 in 3 goes up to here, 1 in 2, 3, 1 in 5 goes even further this way. The steeper the structure, the larger the break parameter. So the steep structures are in this area, the very gentle structures are in this area. The blue lines are for P is 0.1, so that's the embankment, no permeability at all underneath the armor layer. The black ones are for P is 0.5, and the homogeneous structure, really the other one is here. It makes a difference in this area, it makes not a lot of difference in here. So here we see a lot of influence of the wave period. The longer wave period gives you really less stability. Big influence in this area for the more gentle slopes. But if you are in this area, well, then a longer wave period even increases stability. And the minimum here is always the point where you have least stability. Where plunging goes into surging, the collapsing waves, that is the most dangerous point. If you do research on rock structures and you do it in other areas where I didn't look at, and you have new results, then don't go to your own results and make your own formula. Put it into this graph, compare it, and explain why you have a difference. And this is available on my website, so all the data are available, even the graphs are available, and you could put in your own data and compare it. Then a few years ago, I changed my formula a little bit. And that is, in the original formula, there's the mean period. At that time, we used or the mean period or the peak period. But since 25 years, since the 2000s, we saw that the Tm minus 10, the spectral period, which is quite close to the peak period, is a better one. As long as we have a spectrum with one peak, it's okay. Then the Tm is okay. But suppose that we have two peaks, the C and the swell, or we have breaking waves and your peak goes down and you have more flat peak. If you have a flat peak, what is your peak period? So in those cases, then the peak period doesn't work. And then the Tm minus 10, which is simply an average from the spectral energy, is a better one. And it was Prof who came in 2003 with this formula. It looks very much like my formula, but he used the Tm minus 10. So at that time there was not really a comparison anymore, because I used the Tm and he used the Tm minus 10. But in my tests I have still a lot of spectral shapes on paper, and then you can digitize it and you can find your Tm minus 10. And I looked at that, and I looked at the ratios of Tm and Tm minus 10, and I could rewrite my formula. So included Tm minus 10 in the formula instead of the Tm. It changes the coefficient a little bit, because you use another theory, but that's all. So it's not a refitting, it is simply a rewriting, changing the Tm by the Tm minus 10. Now the both formula are more similar. The difference is that he used H2% and I used the HS. So that in deep water there's a factor of 1.4 in between. For shallow water it changes. And he said it was for shallow water. So you have to come up with H2% if you want to use this formula. And what I did is, look, this is my formula, but if you make tests and you have other results, then you have a coefficient here. And the coefficient is the same line, but you can adjust where your curve is. And if that fits your data, then just the coefficient is enough to explain what your tests do. And if you do that for the shallow water, or the Prof data, then the plunging wave of 0.92 here in front, or here in front, or 0.96 here in front comes to that formula. So now they are more equal. Then I come to my last sheets, the data of Prof. He did some tests on shallow water, and we have the data is now free for a number of years, and we looked at it. I also wrote a paper on that. But if you go from deep water to shallow water, the waves change. They may show, so it becomes higher. Then they may break, become smaller. And also the wave period may increase due to infragravity waves. They may become very long. So that means if the wave height decreases and the wave period may increase, then your breaking parameter at shallow water with the same deep water wave heights, the wave changes over the foreshore, then your stability points will shift to the right. The only thing we don't know, if we are here for deep water, certain conditions, design wind waves, if we go to shallow water and our waves change, does it go this way? Does it follow the curve or maybe even increase? We simply don't know. And the other thing is, Prof did only tests with design wind waves, so larger than 2.5% in steepness, but there are waves that are longer. So if we start with longer waves already in deep water, and they come to a foreshore, and they break and become smaller, we go even outside the area of these points. We may end up here. But what way? Does it go up? Does it go that way? That way? What I forgot is, could it go this way? And actually, it does in some cases. I didn't realize, but we did some tests and we don't know why it can also go this way first. So this is, there were no tests a few years ago, there were no tests in this area at all. So we know a little bit about shallow water. We know what waves do. Here we have the wave height, the M0 at the toe, divided by M0 in deep water. And here we have the relative water depth. So this is the water depth divided by the deep water wave height. So this is deep water, and here we enter into shallow and very shallow water. So first nothing happens, and then the waves break, they go down. Here we have the H1/3. So that's from the average from the highest 1/3 of the waves. And it's different from the HN0. So the H1/3 over the HN0 deep, also here around 1. But then you see for some cases, it goes up to 1.4 higher than in deep water. That's the shoaling. We have a 1 in 30 slope, we have a nice long wave, and it shoals and shoals. So we have now a difference of 1.4 between the wave height in deep water and at some point on the foreshore. And after that, of course, it will break again. But we have the shoaling and we have the breaking. And if you go to the ratio for HN0 and HN1/3 at the start, which is this ratio, normally they are the same in relative deep water, up to 2.5, something like that. So here they are the same. But then normally they would go like this for wind waves, but if we have the long waves and 1 in 30 slope, well, it's the opposite of this. H130 is much bigger. So we have to take that into account if you go to shallow water. The conclusion still now, and this is my latest paper together with my colleagues here, and it's free to download from the Journal of Coastal and Hydraulic Structures. The rewritten formula is valid for, say, H over H is deep, larger than 1.5. So waves start to break, not much more than that. What you also found is that H2% is not a reliable parameter if we have very shallow water, because the method we have was based on data with larger values than this. So there is simply no method for this, and if you apply it, it's the wrong one and not conservative. Right now we have two preliminary methods. You could use my formula with H of 0, and that is a little bit conservative, or use a fixed value from a table. So, but this is preliminary. What we really would like to do is to do more tests, also covering swell waves in deep water on the foreshore. That is ongoing research here in Meer. We have 1 in 50 foreshore with Breakwater with 1 in 205 and 1 in 3 slope. The tests are ongoing. We have some results. We discussed it yesterday. At Aalborg, we had 1 in 30 foreshore slope with PS 0.5, so the same kind of structure, but a steep slope 1 in 2 first, and then also 1 in 1.5 slope. So we have some results, not all what we want yet, and we are in the full process of analyzing and seeing what do we see and why does it happen, what is the difference with deep water. And that is the process we have, and this is the nice cooperation that Professor Tomasicchio said, that is what we have. We like research, we know each other, so we do this research. Thank you very much.